Hi everyone! In this video we are going to go over acid-catalyzed hydration of alkynes. So let's start by reviewing the acid-catalyzed hydration of alkenes. So let's say we've got our alkene, and we saw previously that in order to perform an acid-catalyzed hydration, we need to use a catalytic acid, and we represent that with a proton in brackets. So that could be sulfuric acid or phosphoric acid, and that is diluted in water. Now this is going to produce an alcohol, and the alcohol group is on the more substituted carbon, so this is Markovnikov addition. You could also perform this reaction using oxymercuration demercuration. So remember, in oxymercuration demercuration, we're using mercuric acetate, and the mercury atom forms a bridge across the double bond, and then the alcohol comes in and adds to the more substituted carbon. So oxymercuration demercuration, remember, was really useful in situations where you might have rearrangement because it can prevent the rearrangement. Now, what happens if we try to do the same thing with an alkyne? So let's say we have our triple bond, and we're going to add our catalytic acid in water. So this reaction has a really high activation energy. In fact, it's so high that we really don't see any product. So let's just make a note. The activation energy for this reaction is too high. Now, you could add heat in order to speed up the reaction, but you need a lot of heat, and that's actually going to degrade everything. So let's see. So we need a lot of heat, but this degrades. So everything just kind of disintegrates. All right, so how can we perform acid-catalyzed hydration? How can we lower the activation energy? Well, we do have a trick up our sleeves. We can use a catalyst. So we're just going to add another catalyst. So let's draw our alkyne again, but this time I'm going to show all of the atoms. Oops. And we're still going to use catalytic acid and water, but this time we're going to add another catalyst called mercuric sulfate. All right, so quick question. What is the charge on the sulfate ion? Two minus. So then what is the charge on the mercury ion? 2 plus. Okay, so now let's see what happens when we use this catalyst. Well, the mercury ion is going to react very similarly to oxymercuration demercuration. So the mercury ion is going to form a bridge across that triple bond, and then an alcohol will come in and bond to the more substituted carbon. So what we end up with is the following. So we add a hydrogen to the less substituted carbon, and then we add an alcohol group to the more substituted carbon. So again, this goes through a very similar mechanism to oxymercuration, demercuration, and your textbook walks through that whole mechanism. It's on page 417. But you don't necessarily have to know that mechanism for now. So what we've formed here is called an enol. So it's a mixture of an alkene and an alcohol. En, and then we've got alcohol, ol. And I can highlight those important bonds. Now, enols actually exist in equilibrium with ketones. So let's just kind of write that down. Enols exist in equilibrium with ketones. And actually, the ketone is the preferred structure. So even though we have an equilibrium system between an enol and a ketone, usually we have a majority ketone. So usually our mixture would be greater than 90% ketone. Now, the equilibrium between the enol and the ketone is called keto-enol tautomerization, where tautomerization is an equilibrium process. So let's actually draw that keto-enol tautomerization. So the enol doesn't exist for very long. It very easily reacts with acid. All right, so let's just show that it's reacting with an acid. The alkene, again, is very electron rich, so it's going to come in and grab onto a proton. And then we're going to end up with that hydrogen on the less substituted carbon. So again, this is Markovnikov addition. And OH remains on the more substituted carbon, but that more substituted carbon lost an electron when the double bond formed a new bond with hydrogen. So that's going to be positively charged because it lost an electron during that process. Now, in order to alleviate that positive charge, the oxygen can use one of its lone pairs to come in and make a double bond. So then we end up with the following. So now we have a double bond between carbon and oxygen, but oxygen still has a hydrogen bonded to it, so it's still positively charged here. So in order to make this molecule neutral, what happens is one of the water molecules from our reagents, that can come in and grab that proton. Draw a super long arrow here and go into the hydrogen. Normally I try to draw that a little better, but okay, and then we leave electrons behind on oxygen, and we get our final ketone. Okay, now we also have our acid that reformed, H3O plus, formed in the last step. And again, our acid is a catalyst, so it doesn't get used up. It just gets reformed at the end. So this is our ketone. Remember, ketones have a carbon double bonded to oxygen with two alkyl groups on either side. All right, now I'm going to put brackets, or normally I would put brackets around the resonance structures there. I would normally put them on the sides, but they won't fit, so I'll just put them above and below. All right, so ketones and enols are not resonance structures. They're very different structures, but they are in equilibrium with each other. So remember, resonance structures are just two different ways to show the same molecule, which is what I have in brackets. But the enol and the ketone themselves are two separate molecules. Just something to keep in mind. So I would like you to be able to draw this enol to ketone transformation. So the arrow pushing mechanism, because this is going to come up again. It's a pretty important equilibrium process. All right, so this is how we can add an alcohol to an alkyne, but that alcohol ends up becoming a ketone very quickly. Okay, so the enol and the ketone, I just want to add one more thing. These are called tautomers. So they exist in equilibrium with each other. All right, so let's do a couple of practice problems with this reaction. So let's say that we have the following triple bond or alkyne molecule. And let's perform this acid catalyzed hydration. So we've got our catalytic acid in water, and we've added our mercuric sulfate. All right, so what I would like you to do is draw the enol that would result, and then draw the enol to ketone tautomerization mechanism. So you can go back and look at the last slide if you need to, or rewind the video, or you can look back at your notes. Feel free to pause the video as you do this problem, and then when you unpause, we'll go over it together and make sure we have the right steps. Okay, let's go over this problem. So we saw in the last reaction that this acid catalyzed hydration of an alkyne results in an enol. So we know that an alcohol group is going to attach to the more substituted carbon on the triple bond. So that's this one in purple. And the triple bond turns into a double bond. So I'm just going to draw a double bond with the alcohol on the more substituted carbon. And then we also have the rest of the molecule here. So that's our enol. So the alkene alcohol. Okay, and then we're going to grab onto an acidic hydrogen, so a proton. And the alkene is what's going to grab onto that hydrogen. And the hydrogen, which side is it going to add to? Is it going to add to the more substituted carbon or the less substituted carbon? The less substituted carbon. So then we'll end up with our alcohol still intact. But because we added a hydrogen to the less substituted carbon, so we added a hydrogen on the left there, the carbon it bonded to the alcohol lost an electron. So now that is positively charged. And this is where the enol to ketone tautomerization comes in. So the oxygen is now going to form that double bond. So we get that resonance structure. I think this time I can fit brackets around the whole thing. It's hard to draw on a PowerPoint slide all the stuff we need to know. I'll put the hydrogen over here this time. Maybe that'll make my drawing a little prettier. Okay, and then remember in the next step, a water molecule can come in and grab that hydrogen from oxygen. And then we leave the shared electrons behind on oxygen, and then we get our ketone as the final product. We also regenerate the acid. So that's our catalytic acid, and then we have our ketone. So that would be our final product. Okay, let's do a couple more. Now, for these two practice problems, you don't have to draw the mechanism, just draw what the final product would be. Now, if you want to kind of use a scratch piece of paper to go through the mechanism, you can. I'm just going to draw the final products once we have everything listed here. So let's say we have the following. And I'm just going to put little dots for those carbons there. And then I'm going to redraw that because it's kind of hard to see. There we go. That looks a little better. And then let's also look at this alkyne. Okay, and then we're going to perform the acid catalyzed hydration for each of these. And again, I want you to determine what the final product or products would be for each of these. So feel free to pause the video and try this on your own, and then we'll go over it together. All right, so looking at our previous example, we can see that when we start with an alkyne and we perform acid catalyzed hydration, skipping right down to the ketone product, we see that we form a ketone at the more substituted carbon. So we don't necessarily have to draw this full mechanism. We can just know that the alkyne turns into a ketone. All right, so on our starting molecule in the first example, there's two different places it looks like that we could form that ketone. So maybe the ketone forms on the first carbon. And then we get 2 more carbons and another ring. So one product looks like that, where we have the carbon double bonded to oxygen. And actually, I'm going to highlight those carbons. So let's highlight the first one in purple. And we'll highlight the second one. Let's do, no, red's too close. We'll do it in yellow, just to kind of keep track. Now, the ketone also could have formed at the yellow carbon. So let's draw what that would look like. So notice that when you have an internal alkyne, so the alkyne's in the middle of the molecule, that you could have a ketone at either end of that carbon-carbon bond. Now let's look at our 2 products. How are they related to each other? Are they constitutional isomers? Are they enantiomers, diastereomers, or are they identical? They're actually identical. So you could flip one of them around to match up with the first molecule. The other way I know this is we don't have any stereocenters here. There aren't any carbons with 4 different bonds. So they can't be enantiomers or diastereomers. And then they also have the same connectivity. So they have to be identical. So we'll just make a note of that. Now notice that the starting alkyne is symmetrical. Oops. Symmetrical has 2 M's. There we go. Symmetrical. So if you have a symmetrical alkyne, that's going to give you the same exact product at the end. So, regardless of where the ketone adds. So you just get one product at the end. Now, what about our next alkyne? Our next alkyne, you'll notice, is asymmetrical. So this is not a symmetrical alkyne. Now, again, we have 2 different places where the ketone could add because both of the carbons in the alkyne have the same number of substituents. So there isn't a more substituted carbon and a less substituted carbon. They're exactly the same. They just have a methyl versus an ethyl group attached. Okay, so let's show the first product where the ketone forms at the blue carbon. And then if you get confused about how many carbons are in your molecule, you can always number the starting reagent. So let's just number this 1, 2, 3, 4, 5. So then we can count, okay, I have 1, 2, 3 carbons, 4, 5. Okay. Sometimes even I get confused, so don't be scared to number your molecules. All right, so that is the blue carbon that we added the ketone to. But we could add a ketone to the yellow carbon as well. Okay. Now, what is the relationship between these 2 products? Are they constitutional isomers, enantiomers, diastereomers, or identical? So I don't see any stereocenters. There aren't any carbons with 4 different bonds. So they can't be enantiomers or diastereomers. And I'm noticing that the connectivity is different. So on the first product, we have a double bond to oxygen on the second carbon, but in the other product, we have a double bond to oxygen on the third carbon. So these have a different connectivity. So they must be constitutional isomers. Okay, so what this tells us is if you have a symmetrical alkyne, like up above, symmetrical alkynes give one product. But asymmetrical alkynes will produce 2 products. Now again, this really only applies to internal alkynes. So let me write that up above. Internal alkynes, whereas the example we saw on the last slide, so let's go back, that was a terminal alkyne. So a terminal alkyne does have a more substituted carbon and a less substituted carbon, so you really only get one product there. But then when you have these internal alkynes, you can potentially end up with 2 products if your alkyne is asymmetrical. Okay, so this was a lot. I don't want to overwhelm you, so we'll stop here for this video. And take a break, let your brain absorb all this information. And in the next video, we'll talk about hydroboration oxidation of alkynes, and we'll see what that produces. So I will see you then.